Hello and welcome to the LINX Distinguished Speaker Series. My name is Narani Nupuno and I'm the Head of Global Engagement at LINX, and I'll be moderating today's session. So welcome to all of you who are watching this presentation live and to all of you watching it later on YouTube. And for those of you watching it live, do feel free to ask questions, pop any questions you have in the Q&A, and I'll make sure to put them to today's speaker. Don't be shy, as we'd like to have your questions, and it makes for a more interactive session. So the LINX Distinguished Speaker Series is a series of talks gathered here at LINX by experts in the industry who have deep knowledge and often a special expertise and a special unique perspective on a particular subject. And it is my great pleasure today to welcome today's speaker, Todd Underwood. Todd Underwood is a director at Google and leads the machine learning for site reliability engineering. He's also site lead for Google's Pittsburgh office. And machine learning SRE teams build and scale internal and external ML services and are critical to almost every product area at Google. Before working at Google, Todd held a variety of roles at Renesas. He was in charge of operations, security, and peering for Renesas's Internet Intelligence Services that is now part of the Oracle Cloud Service. He also did product management for some early social products that Renesas worked on. And before that, Todd was Chief Technology Officer at Oso Grande, an independent internet service provider in New Mexico. So today, Todd will be presenting all of our ML ideas are bad and we should feel bad. And despite this rather depressing title, I can assure you that this will be both an entertaining and enlightening presentation. So without further ado, I will hand over to Todd. Todd, the floor is yours.
Lovely. Thanks, Narani. Let me present. There we are. I hope everyone can see that. Can we see that? Yes. All right, good. Excellent. So this is the worst LINX meeting ever. The dinner is terrible. Like, I haven't enjoyed the food at all. The drinks are unavailable. This is just not what I had come to expect from a LINX gathering. I feel like we can do better in the future, but we'll do our best here. I will be presenting all our ML ideas are bad and we should feel bad. You shouldn't feel bad because most of you don't have anything to do with machine learning, and so you should just be angry and upset. I do have a Twitter thingy, but I don't use it that much. I also want to point out that this is officially the 214th day of March 2020, and so it's lovely to see you all here today. This is the March that never ends. So let me do a quick introduction of the subject, of me, of you, of life, of the universe and everything, and then we'll get to some actual machine learning content. So here's the agenda. I will cover some basic questions in introduction. We'll weave some philosophy into the presentation, just mostly to confuse people. That you don't need to understand any of that. I will do a hopefully short and extremely basic primer on machine learning, but I've actually found that there is less clear information about what the heck machine learning is than there should be, and it makes most of the conversations about it go somewhat wrong. So let me do that. I'm going to talk about machine learning for production, sort of why would we use it, what do we want it to do. I'll try to add a couple things that are a little bit more network specific, since you all have something to do with networking. I saw there was a network thing in there in your title somehow, something about networks. I'll talk about whether there are any actual good production uses for machine learning that work and future work for someone, possibly you, to do. So here's some basic questions. Who am I? I am a recovering systems and network engineer. I spent 10 years or so working on large ML systems at Google, starting with the ads prediction system that hopefully delivers you little adverts that are somehow related to things you want. 100% of you say you've never clicked on any of them, but my paychecks say otherwise. So I'm not really sure how to balance that exactly, but somebody's clicking on the ads, and I suspect at least some of them are you. I'm based in Pittsburgh, Pennsylvania. It's a wee little town. It's most similar to Sheffield. If you know Sheffield, Pittsburgh is the Sheffield of the US. So you can take that. There's other facts, but those are some of them. This is directed at network engineers, people who want to use computers and networks to do interesting things, but mostly people who want these computers and networks to work well. So one of the things that is tricky about machine learning is many of the uses of machine learning are highly academic and can produce really interesting results, but only in very particular circumstances. We're not interested in those interesting results in very particular circumstances at all. We, I think collectively, are interested in things that work well in our real world experiences, and that's actually quite a bit harder. Why are we here? That's a philosophical question. I don't have an answer to that. You may know why you're here. I do not know why I'm here today. I will actually also try to cover machine learning versus AI, what is actually happening with those terms, but you won't be satisfied with the answer. So let's start with that. Machine learning versus AI. So this is a famous and hilarious tweet from years ago. The difference between machine learning and AI is if it's written in Python, it's almost certainly machine learning. And if it's written in PowerPoint, it's definitely AI. So this will sort of ground you in what people are talking about. No, there is an actual, a little bit of an actual difference. So artificial intelligence is a family of technologies, approaches, techniques that are designed to demonstrate intelligence and produce machines behaving intelligently in a variety of circumstances. So AI is a much more general term, and it's a much more challenging term. Machine learning is much more narrow, and it's the thing we're going to be talking about today. So machine learning is algorithms that can learn from data. And algorithms that can learn from data, I mean, depending on your perspective, that's either fancy and fascinating or actually pretty restrictive and interesting in a way that can be applied. So we'll mostly care about machine learning here versus AI. But I want to point out, it doesn't really matter. Language is about communication, and people do not use these terms consistently, and so you don't have to either. So you can use these terms however you want, and you won't be miscommunicating because nobody's positive what these terms mean in general speech either. I would not get away with saying things like this in a academic setting because they're positive, they know what these mean, so I'm really just talking about how people use the terms. Okay, so let me give a very short primer on machine learning so that we understand what we're talking about, and then I'll talk about some techniques for applying it to production engineering cases. So let's say you're a software developer and you've been given the task by your organization, hey, we've got some data. The data are in the form of pictures. I'd like you to tell me all the pictures that have apple in them and all the pictures that have orange in them. How would we do this in software? Well, I mean, apples are red, right? So I'm going to write some software, and that software is going to look through the picture. We'll try to identify objects in the picture. So we'll find the bits of red that are all together and try to get some sense of like, is this all a red thing, or is this just red scat? Like, is it a red sunset? That's not an apple. But if it's all in one place and it's kind of circle-y-ish and it's red, we're going to call it an apple, right? And then oranges are orange. It's right in the name. There's a hint right there. The oranges are orange. Okay, cool. We're done, right? Everybody all set? Good. So you wrote some software that says, if there's an object and the object is red, it's an apple. If there's an object and the object is orange, it's an orange. Now your software is done. Okay, well, I'll admit we were thinking about the platonic ideal of the apple. So we're looking at the back wall of the cave, and what we saw were red apples. But in reality, some apples are green. And realistically speaking, we all knew that, but we weren't thinking about it because the canonical apple, like the Snow White apple, is the red apple, right? But apples are green also. Okay, so that's fine. So apples are red or green and oranges are orange, and now we're done. Your if statement's getting a little bit more complicated, but it's fine. It's not too bad yet. Down there on the bottom, I don't want to like ruin your party here, but that's a green orange. In fact, all the oranges are green before they're orange, and your boss is like, hey, you actually have to detect the green oranges too. Okay, so that's disappointing. So oranges are also sometimes yellow. So for people from northern climates, you don't have very good fruit. But those of us who grew up in the tropics know there's hundreds of varieties of these fruits, and they're all weird different colors. Okay, so now we've got apples are red or green. Oranges are orange or green or yellow or a blend of those. So color's starting to look a lot less useful. And now we look at this and we're like, look at all of these different weird colors of oranges in varying states of ripeness. Okay, so we have a new plan. This is my new plan. We're going to use the color thing kind of as a hint. We're going to talk about bumpiness because I know for a fact that apples are smooth and oranges are bumpy. That's going to go well. One thing you should be noting is how's your software going now? You just keep adding conditions and you keep adding things to your software. Okay, so here's the problem. That's a wet apple. It's fine. Like apples could like be outside and it could rain, right? You all have seen some rain at one point or another in your lives. To our image processing software, that makes it look like that apple is bumpy. Like, okay, so now we have apples could be bumpy. Also, multichromatic apples like this, it's going to be very difficult to project the surface of this apple with these multiple colors into a smooth space. We're going to think that it's bumpy in the places where the apple is multichromatic. Okay. And now we have a green bumpy apple. And I know it's not bumpy, but it looks bumpy. And there are actually apples that are bumpy as well. I didn't find a good picture of an apple. And actually they're smooth oranges. Like that, actually that orange looks pretty smooth. So now we're in trouble. Now our software is terrible. Now I'll give you a plate of this stuff and you're like, well, which ones of the, what am I, like it's hard to identify the object. And like that thing in the middle, that's a thing in English, we're calling that a lemon, right? So like that's not an apple or an orange, but it's kind of the color of some apples. There's also yellow apples, of course, and it's the color of some oranges, and it's smoothish, but not perfectly smooth, and it's got a weird oblong shape. Maybe we should have used the shape thing, but you can see why this is starting to get complicated. Now, if I cut them open, I have no idea. I stuck a lime there in the middle, right? So as the lime is not an apple, it's not an orange, it's just hanging out in the middle doing its thing. All of these are cut open, so they don't really look like the thing that we were trying to do. And so maybe we need new software about what they are cut open. And so the point is, if you think about writing this software, this is a mess, right? And it's not very accurate. And every time you find another counterexample, the only thing you can do is make your software more complicated and less reliable. Okay, so that's not gonna work very well, but this is in fact what a lot of us do with a lot of software. We say like, oh, we've got a complex space of things we wanna categorize. It could be network outages, or it could be, customer requests. And that complex space, we're going to write some rules. We'll call these rules heuristics. And those rules are going to be moderately rigid, and they won't really categorize everything perfectly. But when we find exceptions, we'll add more rules to them. That looks pretty messy and pretty challenging. It's very difficult to maintain, and it's not particularly accurate. Okay, so this is where machine learning comes in. Let's learn from examples. So here's what we're going to need to make machine learning work. We need a bunch of labeled examples. So an example is something that you are trying to learn about. In this case, the examples are images of something. A label is a known category that applies to that example. So in particular, a label would be a picture of an apple, would be the example, and the label apple is the label onto that example. Then we need a system for updating some kind of data structure about what we've already seen and what we know. Facts about the examples are called features. You don't really need to know that, but it's a thing. And that where we're going to store these is something we'll call a map or a graph. It's going to keep track of what we've learned. So that's the data structure that we're building. Then we need something machine learning folks call a cost function, but you can think of it as an accuracy function. What is the thing you're trying to maximize? What is the thing you're trying to maximize or minimize, depending on how you think about it? How will you know when you've done a good job versus a bad job of categorizing these things? And that cost function really needs to have something external from the system, because that's the feedback. That's where you say like, hey, I called it an apple, but actually it was a pear. And so I get dinged on that and my value goes down, and I update my results to try to clarify, no, actually that is a pear. Okay, so there's lots of ways of doing this. People will say deep learning, people will talk about neural networks. All of these things are interesting. If you care enough about those, you've already taken the Coursera course on gradient descent, and you've already taken some like online courses on machine learning, and I don't need to tell you anything. And if you haven't done those things, you may not need to, because the stuff moves pretty fast and you either specialize in it or you don't. And it may not be the thing that most of you want to specialize in it. So that for purposes of this talk, it actually doesn't matter how you're storing that. You're storing some stuff about what you've learned. So now we've got this idea of machine learning. We're going to learn from examples. We're going to have labeled examples, and we're going to try to do something with it. Well, what would we do with it? Like what, this is in fact how venture capital works, right? Like we've got a solution, let's go find a problem. So we've got this idea of machine learning. Let's figure out what can we do with this machine learning. Okay, good. So what production-y, networky kind of thing is it for? Well, here's some ideas. We want machine learning to do annoying, repetitive, but important stuff. So stuff that your operations staff have to do, they hate doing, that's important that it be done, but it's utterly uninteresting. That's actually just what computers are for, right? That little snippet between like, it's useful, but it's not interesting. Cool, okay, that's what we made computers for. God gave us computers to do useful, uninteresting things. So for example, monitoring maintenance. So Everyone here has some monitoring. Your monitoring will go off at some threshold. Those thresholds are chosen by some combination of carefully thought out statistics in some cases, dark magic in other cases, and anger at 3 a.m. in other cases. So when you think about how you actually select your monitoring thresholds, the single most common reason something is set at X is because it was a little bit below X the last time it paged someone in the middle of the night and they didn't like that, so they bumped it up. That's a terrible reason. Like that's not a principled reason why. So if you're like, I will alert when this link is more than 92% full. Well, the second it pages someone at 92%, but it's kind of been flat at 92% for 6 weeks, they're going to change that to 93 and they're going to go back to sleep. And now it's 93. And 8 months later, when someone says, why is this at 93%? You're going to say, like, I don't know, I think it paged someone when it was 92%. So maybe we want computers to do that instead of people doing that. Okay. Alert suppression and analysis. So flagging false positives and suppressing them. Like all of our alerting systems have false positives and we may want to suppress them. That's fine. Capacity planning and prediction. This is hard stuff, but for people who operate relatively large networks or computing systems, you get the stochastic stability of demand and you can predict some aspects of where things are going. But the larger and more complex your deployment gets, the more tricky it is to figure out how to divide that up into individual bits of capacity. So we may want to say like, hey, look, I know that in the next year, we're going to grow 14 to 18%. But what I don't know is whether I have enough capacity between A and B. I'm like, okay, well, maybe the computer could do that for us because that sounds kind of tedious, but also pretty important. Validation of canaries. So you're rolling out a new version of software to network devices or a new version of software to computing devices. You want to know, I'm going to roll this to a couple of places first, and I want to know, is it working well? And more than half the time, what we do is we roll it out and we wait. But what are we waiting for? Like we're waiting for it to blow up in some obvious way. We're waiting for somebody to complain or not complain. Like waiting is just a dumb reason. It's not a principled reason to figure out, did we break something? So what if we could just roll it out and right away know, oh, this is terrible, roll it back, or right away know, this is fine, keep going. If we could do that with confidence, that would be amazing. And machine learning might be able to help with that. Root cause analysis, so you have an outage, what actually caused it. There's some principled ways that machine learning can help with that. And then automatic service and resource scaling. So this is a big one. If you have resources that can be moved between different service classes, sometimes when you start to see a spike in one kind of usage, you can move resources automatically into that. And that's less true for anything that has physical properties with long lead time like network links, but it is true for other kinds of resources, and many people are able to do that. So that sounds appealing, right? And then we would just not get paged in the first place, and we would never have the case where we updated the threshold to 93% for no good reason, which would be great. Okay, that sounds great. We should just do that. That's the plan, end of presentation. No, seriously, none of this is gonna work. All of these are terrible ideas. I know I convinced you there were good ideas because I talked each one through and it seemed sensible, but they're actually not mostly doable, which is super sad because now I've just raised your hopes and then crushed them, which is my job here today, is to crush hopes. So why can't we have this? Well, let's talk about why we can't have this. So let me talk about categorizing and prioritizing tickets. So tickets come in. Tickets come in from your customers, tickets come in from your computing systems. Like most of our tickets are filed by systems, not by humans. So you get some sort of bugs filed by things that file bugs to other things that file bugs to other things. It's just the computers talking to each other. But somewhere at the end of that is some human who's like dredging through and categorizing each of these. And so now you have like 14,000 tickets a year coming into some system. And out of that, maybe like 90 of them are super interesting and important. And the rest of them are somewhere between like vaguely interesting, but kind of useless and completely useless and never should have been tickets. Okay, so here's the idea. In an attempt to focus and prioritize work, you put all your tickets in a place. Like many people have a ticket system. Sadly, for most of us, most of you have multiple ticket systems. You should probably just have one and put it all into one place. Humans and computers create too many tickets. We spend all the team's time triaging and categorizing those tickets. So instead, we're going to use machine magic, and then we will profit. It'll be delightful. This sounds great. Okay, so the ticket handler algorithm is going to look something like this. We figure out what it is about a ticket that most predict the ultimate ticket handling priority it gets. So we have some system where tickets get filed, they go through some process, and then some human says, oh, this is a priority 1 ticket versus a priority 2 ticket versus a priority 3 ticket, a Sev 0 Papa ticket, right? So that's fine. Okay, So we're going to get labels, remember, from existing tickets. We have these existing tickets, and they're labeled by humans because they ended up having some priority, and they closed in some state. Well, I mean, hopefully somebody did some work at some point. So some of them were closed, will not fix. Some of them were closed, obsolete. Some of them were closed, fixed, whatever. You will have some statuses, and you'll pick the ones where it was a good ticket, had a correct priority that was high, and we fixed it. So it was a ticket that like led to useful work being done. That'll be a positive signal for whatever things about that ticket. Could be time of day, could be who filed it, could be the words in the ticket. And then a negative signal will be anything else. Like this ticket, nobody ever worked on, nobody loved it. And it's not perfect, but you can sort of see that. Okay, we're gonna train a supervised learning model. Don't worry about what that means, but we're gonna train a supervised learning model on these labeled examples using some features we figured out were the most important features. Again, I'm thinking of time of day, category, customer, words in the ticket, who handled it, you know, things like that. Okay, and the model is going to set the priority for the ticket. So the idea here is ticket comes in and the model says, hey, this is probably important. Like here's 123 that also came in the last 43 minutes, but this one you should look at first. That actually sounds pretty useful, right? So now all the tickets are at the right priority on ingress or close to the right priority. So let's take a break for a joke, because you just like, I feel like it was too hopeful here. So I'll tell a joke and then we'll get to like why this doesn't work at all. So machine learning algorithm walks into a bar. Bartender says, what do we have? Machine learning algorithm says, I'll have what everybody else is having. So that's the first part of the joke, because that's actually funny, because that's all machine learning does is just like repeat things that's already seen. But then the machine learning algorithm orders a coaster, because that's in fact what everybody else has. That's the only thing common among everyone else. And that is deliciously funny for a bunch of reasons, but in particular, it's funny because that is actually roughly how stupid most of ML is. Like it's completely unable to distinguish the difference between a Guinness and the coaster beneath the Guinness. And since more people have coasters than have Guinnesses, it's going to order a coaster. So what, if anything, is wrong with this idea? Okay, so first of all, there's probably a better way to fix this problem. And the reason I bring this up is ML is delightful and hyped and wonderful, and my company makes money selling you all ML services, and I'd love for you to come use them, but it's actually very expensive. It's very expensive because you need to process a lot of data, and we'll get to that in a second. So if there's a cheaper way to do it that's even close to as good, you should probably use that first. So one of the cheapest ways to fix this problem is stop your systems filing so many tickets against each other. Like most of us have systems that are filing tickets against other systems that may themselves file tickets against other systems. If you have that, just reduce your false positives by a lot right there. I know that sounds easy, but it's actually, or sounds hard, but it's actually easier than doing this with machine learning. So if most tickets are currently being ignored or unworked now, right now we have almost no signal. So what we don't know is how many important tickets are in the mess of tickets that aren't being handled at all. How much important work are we dropping now? So we actually have a risk that if we did this approach, we would train a bad model, a model that we would not be happy to have. There are not enough examples. I didn't talk about this that much, but we need a lot of data to make machine learning work. So let's say you have a terrible case of this. You might have 100,000 tickets you could train on. That's not even close to enough to get really good results. And honestly, if you had 100,000 tickets, you would be so sad that you would not have enough emotional energy to get your way to machine learning anyway. So you would probably need 1 million or 10 million tickets to really probably get reasonable results here. And here's the other problem. There's not enough labeled examples. Like how many tickets did the humans in your organization handle in all of the last year? I hope it wasn't 1 million. I think it was probably 100, order of 100, order of 100. 1,000, 5,000. It's not thousands, and it's not tens of thousands or hundreds of thousands of labels in tens of millions of examples. So remember these things. If there's a better way, if there's not enough examples, if there's not enough labeled examples, this is your cheat sheet to why all of these ideas don't work. Sorry to say. All right, so that didn't work. That was disappointing. I mean, it could work, but it looks really expensive and it looks like it's not worth it. Let's do automated root cause analysis. So given an incident and an outage and a page, like tell us what caused it. So something went wrong. We had some kind of outage and we got some sort of alert, and all we want to do is trace through monitoring to figure out what happened. So here's the basic idea. Outages are difficult to troubleshoot either in the middle of or even afterwards. So many things can contribute. The best production engineers and network engineers are way faster than the least experienced ones. We all know that. Like the person who wanders in is just like, Oh, it's that. Cool, but like, how could my like 6-month tenured new engineer handle that? Hard to say, right? Outages last too long, new staff take too long to train up on complex systems. So we're going to use machine learning to solve this, right? We're gonna train on features of an alert and an outage and an incident. And we're going to, during an outage, say like, hey, we think this is probably this thing, to direct attention to it. So that sounds pretty promising. So what's wrong with this? So there may be a better way to fix this problem, again. So heuristics are frequently better way to fix this problem. They're a little bit rigid and they can go stale, but they're actually a pretty decent way to fix this problem. We have insufficient information right now about the accuracy of what we already do. So we don't know how accurate we are at currently categorizing outages. So if we train a model on that, we will end up also replicating that lack of accuracy. We don't have anywhere near enough examples. Oh, I should say, I hope you do not have anywhere near enough examples. If you have 10 million outages, that might be enough to really train up a good model on this. But I'm hoping many of you have fewer than 10 million outages and way fewer than that labeled examples. So how many outages do you have that are representative of your current production environment that are labeled in the recent past? And most people, it's going to be dozens at most. So this is not enough for a machine learning model to really get much traction. Okay, that canarying thing. So that didn't work out. I feel bad about that, but that didn't work out. I'm all here about false hope. But the canarying thing I have a good feeling about. So we're going to automatically detect bad pushes of software under a huge variety of circumstances. So we've got some software change. We all do continuous integration, continuous deployment. We love it. We're pushing software to production all the time. We're updating everything all the time. But occasionally, and I know this will shock all of us, sometimes software engineers make mistakes and sometimes software is not perfect. This is a surprising thing, but we've recently learned it to be true. Okay, so we're gonna write tests. We're gonna have smoke tests and integration tests, but our tests are also not perfect because tests are just software. So that's too bad. So we need to catch stuff that's broken that the tests don't catch. And actually our monitoring is not perfect, and that's the killer, right? So we roll out new software, the tests don't catch it, the monitoring doesn't catch it, so now we push bad stuff to our users, and then our users will suffer. So we're gonna use machine magic, it's gonna be great. What's wrong with that? That sounds delightful. So you should add more tests. Like when in doubt, you really just need more tests. Tests that are rigorous, that emulate the actual behavior of customers, are way easier to write and they fit within your current environment. You should have service level agreements, service level objectives, and you should run tests to match those. If you don't have those things, most of the rest of this won't work. And if you do, you probably don't need the machine learning yet anyway. There's a low certainty of which pushes are actually bad. And here's one of the interesting things you might not know for quite some time. So you might have a problem that you create where you push some new software, you push a new router image, you push new configuration. 7 days from now, it turns out that actually caused a significant problem for a very small subset of traffic or for a very particular kind of customer. That can happen. Well, now if you're using the machine learning thing, you've trained up that model that this was an awesome push and everything was good about it. Well, that's terrible. That's not good. Okay. We also don't have enough examples. So how many of you do deployments of any given thing more than 100 times per year? Not that many, 1,000 times, 10,000, like we need millions of these. So that's, unless you're deploying multiple dozens of times a day, you won't have enough examples. We definitely don't have enough labeled examples. How many good pushes, how many bad pushes. All right, so automated canarying analysis, especially for networking environments, definitely not gonna work. That is unfortunate. This is getting tedious. I pointed out that these would come back. There they are. Okay. So I think that most of what people talk about when they talk about machine learning is really marketing machine learning. They're selling you something, and that's fine. Like, my teams run the Google Cloud AI services, and so sure, I'd love for you to use those, but you should use those when they're worth it. You should use those when they make a difference. I think a lot of people pitching ML just want you to play with machine learning, but it's not going to make a measurable difference to your business, to your organizations. And so I have this principle, like, I like math. Some of you like maths. You should use the least amount of it you need. I should have made the maths plural for this audience, and I do apologize for that. You should use the least amount of maths necessary. You should use exactly as much maths as you need to, but no more. And all machine learning is very, very complicated maths tied to a data structure. And so I think save the fancy maths for the very, very, very big problems. And sadly, most of us have really tractable problems that have better solutions for other things. So what are the actual plausible production uses of ML? So is there anything it could do for us? It's not useless. I wouldn't have a job if it were completely useless. And I don't want to be hypocritical here. Like Google and Baidu and Amazon and Facebook and a lot of people use machine learning for almost all of our stuff, or at least sprinkled around everywhere. But even so, it's very expensive, and we're cautious about what we do with it. And we want to make sure we get enough value for the compute and the organizational complexity and the software complexity we build. So if we were to find plausible production applications for machine learning, we would need an ML-shaped problem, so something that can be clustered or categorized or predict. That's fine, we've talked about that. We need loads of data, tons of data, scads of data. You cannot believe how vastly, hugely, mind-bogglingly much data you'll need. Like, you need a lot of data. You need lots and lots of labeled examples. So you need to not only have the data, but you need to have categorized a lot of the data. And that can be a significant amount of work. There are services like Crowd Compute, like Mechanical Turk, where you can hire other people to categorize your data, but you've got to categorize the data. You need to have some ideas of the feature, what about the data is predictive, and then you need to have some way of evaluating what I called previously a cost function or an objective function. How well are you doing so that you can improve on that? So here's the pre-work you'd have to do. You need to gather your data in a place. If your data are in multiple places and you can't access them all from a single system, you really can't do much at all. So you really need to put your data in a place, your data about the production systems. So here's some recommendations I have for what people can do now. I think that if you have an interest in adding machine learning in some sort of sense to your production environments, you should be thinking about what sort of use cases those are and gaming those out, making sure that there is not a simpler solution, talking to people who know your infrastructure, talking to people who know how the data are stored, and think about useful ways to manage and automate some of those things in advance of that. Gather your data in a place, and then do some basic learning about what works well in machine learning and what doesn't. There are certain kinds of things that seem trivial, and then there are other kinds of things that seem just as trivial, but are like fundamentally impossible. And so I think thinking through the problem and then consulting a few machine learning experts and say, is this one of those that looks easy, but is actually incredibly hard? Or is this one of those that actually is just easy? And there's some things, and things move around in that. There are things that we used to think of as being basically impossible that are now super tractable with machine learning. And there are things that are still basically impossible that seem like they should be easy. So here's an example, driving a car, right? So most human beings can learn to drive a car. It really isn't, I mean, most of us do it badly, but most of us can drive a car, and like the world seems to work with driving cars. Computers can't drive cars very well at all. So in Pittsburgh, the city I live, we have 4 self-driving car companies whose company name starts with the letter A. So we have a lot of self-driving cars on the road, and they're just terrible at most things. Like they can't figure out how to turn left in front of other cars when the car is coming too fast. They're really good at not hitting pedestrians and cycles, and I think that's great, but they're mostly not good at most of everything else. And when you look at it, you really get the sense of, we're going to get there, but it's going to take 10 or 20 years. And that's an example of something that you feel like we've been doing this now for 10 or 20 years. We should be further along, and this is how far we've gotten. So here's some future work for somebody more clever and more ambitious than me. It would be useful to create a careful categorization of the kinds of problems that are amenable to ML for production uses and the kinds that are not. So that would be sort of an ontology. The epistemology is, what do we know and how do we know it? So what are the kinds of data problems that about our infrastructure that are amenable to this, and which are the ones that are not, and mapping those data onto the ontology. We don't need any metaphysics. I just put metaphysics on there for completeness. Nobody needs metaphysics. It's not important. No metaphysics. Okay. Last thing. So I did recently with my colleague Steve Ross give a presentation at the OPML conference that digs into a few of these topics in a little bit more detail. And like, I'll give you the 2-second overview, which is actually that auto-scaling one. If you remember, I had mentioned auto-scaling. The auto-scaling one, we have some good results recently that suggest that it is an area of bright spot in the area of applying machine learning to production. So the basic flavor of that is you have a lot of if you have a medium-sized serving infrastructure, let's say, the question is like, should I add more servers to serve this web page? Should I take away servers to save money, right? So you have some sort of a cloud flexible environment. You will get a lot of examples because you might do that dozens or hundreds of times a day. You will get lots of labels because you will know when you run out of capacity and you will know when you spent too much money. So your bill is a negative label, I spent too much money. And like serving errors is a different kind of negative label, I didn't have enough capacity. So you get automatic labels and thousands of examples per day or per week, depending on how often you scale. And so there is a way to turn those data into a reasonable machine learning approach where you can tune your risk tolerance. You can say, I'm pretty excited about this one. Like I'm willing to, like, I want to save money, so I'm willing to throw a few errors in order to save money, or vice versa. You're like, this is super important to me and I'm willing to waste money in order to ensure that I serve this web page. And by tuning those parameters, you could get a machine learning model to just run your capacity for you. So that one looks hopeful, and we're using it inside of Google, and other people have gotten some good public results that are published, and we cited them there. Aside from that, our other suggestions here stand. They're really, sadly, not very good uses of machine learning for these particular problems. So the last point I'll point out is I did suggest that you all collect the data in a place so you could start doing this. But one of the things I noticed after preparing this presentation is that nobody wants to fund that, including my boss. My bosses don't want to fund that either because they're like, well, why would we do a bunch of engineering for no value whatsoever? Because putting your data in a place and having it all in the right format that you could do some machine learning on it, that's work, right? And so not surprisingly, your bosses don't want to pay for work that has no value proposition. So I've modified this a little bit to say, come up with something you can do that's even a tiny bit useful and start doing that, because without that, your bosses won't let you play with this stuff. So if you want to play with machine learning, come up with anything you can do that's at all a tiny bit useful, and then use that to segue into bringing all of your data into one place. With that, I leave you with a cute kitten to distract the audience so that no one will ask me any hard questions.
Thank you so much for that, Todd, for that entertaining and also still slightly depressing talk. But just a few reactions, and I'll allow the audience to throw a few questions at you as well. I really liked the start of your presentation with the categorizations, because it's one of those things that seem very simple on the outside, but I think, all research shows that those things are cultural, those things are, language bound. There was this psychologist, Vygotsky, who lived at the turn of the century, who basically showed that language forms how we categorize people. So he studied, for example, farmers in Russia and found that they categorize tools very differently to people who are educated. So educated, literal people who could read, they categorize according to categories, while the farmers categorize them according to where they're used, for example. Mm-hmm. So those things I think are often easy to forget, because you think that, oh, well, an engineer can just, figure out what categories we have and just give those scripts to the machines and the machines can work it out. But clearly it's not that simple.
No, and I think one comment I would have on that is, it's one of the most important reasons that working in machine learning and artificial intelligence need to be more democratized. Because what we found over and over again is when teams of wealthy male first world engineers build ML systems, they build terrible ones, because they're just like, oh, everybody's like me and they have the same thoughts about the things and I'll just do the thing. And then they deploy it to the rest of the world and are shocked when that doesn't work for whatever reason. And so I think, even more important, so I think our organization should be more accessible to people from a huge variety of backgrounds, from geographic and language and gender and racial and ethnic backgrounds. But for machine learning, it is critical for the future of society that they be so, because this stuff doesn't work if homogeneous teams of people build it, for exactly the reason, because they would make up categories that make perfect sense to them and zero sense to someone from Togo or someone from Australia or someone from Hong Kong.
Yeah, right. No, and so then the other Pearl, if I want to turn it into more of a philosophical question, you know, so one thing is diversity and have a, you know, diverse representation in the people making it. But the other thing is it really a great idea to have engineers make decisions about what data should be fed into, you know, these machine learning and what assumptions we should make? Should we not have people with different skill sets, philosophers, ethicists, or sociologists, or even lawmakers? I don't know. And would that not actually yield better results in the end?
Yeah, I think it's a really good and an important question. I think, so there's two sides of it. So one side of it is on the data collection side. And, you know, when I talk to American audiences, they're puzzled about this, but I think European audiences understand that data is as much a liability as it is an asset. Right? When you have data, you have to protect it. You have to protect access to it. You may have to delete it in the future. You may have to answer questions about where you got it and why you got it. And all of that's as it should be, but it means that many organizations who think, I'll just store everything and figure it out later, that's a terrible plan, because now you just have this massive liability and you don't know what's in it. And it's even a liability separate from privacy or privacy-related reasons, even separate from legal reasons. If you have a bunch of data and you don't know where it came from, it's actually not that useful. So the data collection side definitely needs a strong legal framework and a strong privacy framework. But I would say also on the machine learning modeling side, what we have found is that you need a public discussion about what you're going to do and for whom you're going to do it and what circumstances you're going to do that. And that does need to be a conversation that's not primarily about engineers building a system, but primarily a conversation that's about organizational purposes, but also ethical purposes and societal purposes. And so, you know, Google ended up publishing our AI principles for exactly that reason. We had well-meaning engineers just running fast, doing things, and they seemed perfectly sensible to small teams of people who were perfectly, you know, able to do those things. But when we would raise that up in visibility, either to the public or even to senior management, they were things that we actually didn't support and didn't approve of and weren't encouraged by. And so I do think, like, I think part of this, you need an ethical framework, and for that you do need ethicists. So finally, the ethicists will have something to do.
That's a good thing, and we all need to practice, I'd say, ethicists, because I think that's another challenge for all of us. So I see a few questions in the chat, and I'll go to one of them. So one question is, can I use ML for net flows in order to detect successful connection?
Yeah, so what I would say is, let's bring back the framework of how will you know if machine learning is a good application for it. So first step, do you have enough data? NetFlow sounds pretty good for that, right? You will get a lot of NetFlow records. In fact, most people spent the better part of 10 years sampling and not writing down their NetFlow data because it was too much. So that sounds great. Okay, NetFlow data. The second question is, do we have a labeling function that will produce enough labeled data? So when you want to detect a successful connection, the first thing you need to do is have a bunch of examples of successful connections. So that might be trickier, but you might have a way to do that. So you might have a way, so the canonical way to get these things, these sort of labeled examples, is to have the answer later than you want the answer. So if we have a system where we're like, I will be able to figure out at some point in the future whether this connection was successful, but the point is I want to know right now based on these data, that would be perfect. So if you join NetFlow data with, say, server logs, right? So if you have this, if you have some concrete evidence that that was a successful connection, then you can use that to then predict or categorize which NetFlow records coming in represent very likely successful connections in the future. So I would say that's actually probably possible. Yeah, that doesn't sound terrible. That's interesting. I didn't expect people to have good ideas. This is good.
Well, God knows what that will lead us. So another question from Ivan Beveridge. Is there a suggested way to store data that can be used for such machine learning? How would that be decided?
Yeah, so it's actually a great question. The canonical answer is column oriented. And the reason for that is, so if you think about your data are in rows and in columns. Rows, you can think of it just as, you know, a spreadsheet. So rows in our world, rows are usually a single sample. So a single sample that has multiple aspects to it. So you can think of a log line, for example. There's a timestamp, that's one column, and there's a type, a log type, that's another column, and then there may be, key value pairs or a piece of data that you're reporting, and then another one, and then another. So if you think about that, what usually happens is you'll have moderately large log lines, but only parts of that log line will be relevant to your model. And so as a result, if you store things in row-oriented form, you end up reading a lot of data that you wish you hadn't had to read. And so what most of us do is we do some pre-processing to store data in column-oriented formats so that we can simply read the columns that we think are relevant. And then, you will join across columns. So you'll say, like, at this timestamp, this key value pair happened in this log type. So there's 3 pieces. But that log line could be like 3 kilobytes. It could be, 100 kilobytes long, and you just read 3 little pieces. That can speed up your training by a factor of huge. Now, for other things, you just want a pile of data, and it doesn't actually matter. So, if you're training on images, you're just going to read big images. If you're training on video, you're going to read big video. What most of these systems have as a fundamental feature is that there is some data pre-processing. So in order to read the data and make use of it, you need to do something with the data. So a great example is in the one I talked about, image processing and identifying oranges and apples. You have to do edge detection first, and you have to do object detection next. So if you haven't detected edges and objects, and you're just looking at red and orange, you can't make any progress at all, and your model will be terrible. Now, the model I pointed out was not going to work out, the heuristic model wasn't going to work out well anyway, but you should start with edges and objects, and that's a form of pre-processing. Similar with video, you're going to have to do some pre-processing in order to get features out of it. So yeah, so I would say it's column-oriented and do some pre-processing that is targeted at the specific task that you're attempting.
All right, great. Interesting. Okay, another question from Ivan. How's the best way to address, say, incidents with ML? Using Syslog data is presumably likely to provide a complicated result, but only picking out known logs that have demonstrated an issue previously would seem to limit the use of the ML.
Yeah, so I think again, like what you're trying to do is have enough of the data that is predictive of the thing you're trying to predict and know the answer for some of it. So I think Syslog data is probably a good place to start. And the question is, do you have enough accurate labeled examples across the variety of problem types? And so that's really where I see the logs processing examples fail, is that if you think about what shows up in your logs, everything that goes right and wrong shows up in your logs. And so it's not right to think of it as, 10 million log lines. It's not 10 million log lines. It's 100 of them about this one kind of thing that goes wrong, and 1,000 of them about us doing well at this other kind of thing, and 20 of them that show us having this different kind of failure. And so you don't actually often have as much data about any given thing you want to predict as you think you do. So if you have a very homogeneous service where you're, I'm serving one web page, that's all I'm doing. Or like I'm running the Yo application. I love the Yo application. My user ID is Todd Under, so you can send me Yos. That's still an application, still works, very important. But I think if you look at a simple application where all of your log lines are about whether that application worked or not, you're in business, right? Because now you have a lot of data, you figure out where it worked, move on. But I think most people's syslogs are much more heterogeneous than that. So I would be skeptical, intrigued, but skeptical.
All right, thank you. Can I just pick up on one of the things that you talked about the pre-processing of the data, and clearly you have to do some serious thinking about how to pre-process the data in order for that to be useful then when you'll be using that data. But what are your thoughts around the layers of abstractions of data and assumptions that you sort of build into a system? I think we all have this sense, or we often assume that if it's processed by a computer, then computers are rational and logical. So whatever output comes out is probably more trustworthy than if someone else sits there and sort of makes judgments, and we forget that, you know, there are assumptions and there's processing that has happened before, long before that output comes out. So what are your thoughts around both the sort of the risks that we can just sort of add so many layers of abstractions to this data that we don't actually know, or whoever takes the output doesn't actually know where that came from, or but also are there do you have I don't know, policies or guidelines internally about how to make that transparent, or how you can make it possible to go back and look at what data was actually put in, or what processing actually happened when? It's not a question, but
no, I think it's a super important question. So I'll say a couple of things. There's a thing called explainable AI, and so it's a subspecialty in the machine learning, artificial intelligence community, whose initial, you can think of it as like principal component analysis, but for machine learning models, where you just go in and you say like, okay, so you said don't give the loan for the home to Narani. Why did you say that? Like, what were, not exactly why for her, but like, what kinds of things dominated your decision? Was it about her income? Was it about the place that she currently lives? Was it the time of day? Was it what, you know, the loan officer had for lunch today? Like, why did we turn down this loan if we're sitting here at Evil Bank Co? Right? And so
can you find out, because if you find out, can you let me know, because I was wondering exactly that.
Is that true? We turned you down for a loan? I will look into it. Yeah, so we'll take that as an action to follow up on why we turned you down for the loan. But I do think, so that's super important, but it is tricky because, and I think you were highlighting this. So let's say if we know why we did it, it still doesn't make it right. So let me give an example from the awful world of US racial politics. So we go in to determine whether we're going to release someone from jail pending a trial. So we can't put them on trial. They've been accused of a crime. And now we're like, well, should we hold them or should we release them? It turns out that when you train machine learning models on that, the data set that they had available was, is this person likely to be taken custody or have some kind of negative interaction with law enforcement between now and their trial? If they are, we'll just keep them in jail. And if they're not, then we'll set them free. Cool. Turns out if you have brown skin, you're very likely to have a negative interaction with police, regardless of whether you're going to show up for your trial, regardless of whether you were guilty of that crime you were accused of. And so the model simply said, based on this thing, it's not about race. I'm not saying keep them in jail because they're brown. I'm just saying keep them in jail because the cops are going to like charge them with another crime before we get to trial. Right? But that thing that we're predicting on is actually standing in for another problematic thing. So all that model does is say, well, we have a racist society, so we should really double down on that and continue being racist. But that doesn't make any sense, right? Similarly, loan data is usually tied to geographic data. So if you live in a postal code that has mostly poor people, then you can't get a loan even if you have plenty of income. So now we're saying, oh, it's just the model just said that people from that postal code tend to not do well with these loans. And so we've had another bias. So I guess what I'm saying is, even when you know the explanation, you might not identify the bias that the explanation is a proxy for. So all of this is to say that ethical AI is super tricky, and it is important that people have organizational and thoughtful frameworks that they use to approach this. So even when you try to get it right, sometimes you get it wrong, and you should be aware of that.
Yeah, no, that's super interesting. And I mean, what you're describing is actually in place in quite a few places. And I know even in some states in the US, they're now even providing tools to judges to help determine the length of the sentence that they should be handing out, and yeah, unless we actually know how that tool works or what data gets put into that, then it's very difficult to question those structures or those decisions.
That's right. And I think we all just have to remember, like, we own these results, like as citizens of our various communities and countries. Like, we have to believe in these things, and if we don't, we should talk to decision makers and say, like, you know, and I say that to this audience because nerds are powerful in this respect. Like when we say, hey, I use computers, I know how this stuff works, you shouldn't use it, and here's why, people get freaked out and they listen to us, because most people are like, I got my kids' iPads and we should use the ML to figure out who goes to jail. It's all fine, right? No, it's not fine.
Yeah.
We should be thoughtful about that.
So then on a more positive note, I see a question in the chat. Do you have any examples of where you think ML has improved the world?
I mean, I think that there's actually quite a lot of them. I think, you know, so it's not without problems, but I think the photos and the photo classification stuff is amazing. You know, I remember, like, you can just search for people in your photo streams. You can identify scenes in your photo streams in a way, like, you know, so now we're all drowning in these lovely photos. So I wanted to find a particular picture of my daughters dressed up in ballet tutus. So I can just go into my photo archive and search for the word ballet. Now, I've not labeled anything because I'm complete lazy sod and I don't label anything. But so ballet brings me pictures of me and my family going to the ballet because it happens to know that that is the ballet. So that's cool. But also pictures of my daughters in tutus running around in the backyard because they're like, that's a ballet thing, right? And so like that, I think that's amazing. I think that there are many aspects of how we run computing systems that are significantly improved by machine learning. I think that like machine learning for vision has been incredible, especially in geo applications. So like the ability to identify road signs, you know, so most cars now, any car sold in the last, you know, year or so, and certainly some luxury cars before that, when you're driving along, they can just read road signs and they can tell you like, hey, the speed limit just changed. This is a 40-kilometer-an-hour zone. Like you need to go slower, right? And your car, like that could be in the map, but that also can just be the cameras on the car. And I think that, so I think that in the field of computer vision, that's amazing. And it's helping with, it's unfortunate for my colleagues who are radiologists, but I think like ultimately it's going to get rid of most of radiology because we will train computer models to recognize cancers and to recognize anomalies and broken bones and other things. I think there'll be a long period of cohabitation of, you know, there'll be cooperation of experts and computing models, but I think over time that'll be great. So I think that there's definitely some things that are incredibly hopeful, but I think we have to be careful because that same kind of computer vision can be used to do drone-based assassination, right? Or can do like some truly terrifying things. And so we need to be cautious about how we apply those.
Yeah, interesting. Well, thank you very much. I think I still have a bunch of questions for you, but I think we're up to the hour. One of my questions was actually how many more captures we're going to have to do before the machines learn what a traffic sign is. But maybe you can email me that separately, or
I will
we can
route
tweet
all the
about it later.
captures to you, Narani. I'm routing all the captures to you from now on.
Thank you, I appreciate that. And so with that, I will say thank you for a fantastic talk, Todd. I found it highly informative and very interesting. Thank you for all of you who participated live and asked questions, and for any of you watching it afterwards. Please do keep an eye out on the LINX website for upcoming presentations and tutorials. We have some really interesting speakers and talks coming up, and so make sure to register for those. Now they're all free and open for anyone to listen into. You will also be able to watch past talks from there and on the LINX YouTube channel. So with that, thank you again, especially to you, Todd, for taking the time to share this very interesting presentation. It's been a real pleasure listening to you. And with that, I say thanks to all, be well, stay healthy, stay safe, and hope to see you all again very soon.